All right, so one of the challenges that you're going to find is that as you go through and convert stuff from the time domain to the S domain, you end up with a lot of stuff that kind of looks like this, right? You have stuff that's appearing in S, but that has a bunch of these factors multiplied together in the denominator. Just sort of the way these things work out. So in order to solve this, it's really not possible to take the inverse Laplace of this thing. What is possible, if you look back at our table, is if you have these individual little terms here, like if you have some constant over, say, one of the terms that might appear in the denominator, it's easy to take those inverse. So what we want to do is actually figure out how to get these into what looks like, some constant over S plus 1 plus some constant over S minus 1 plus, right? You want these things to kind of be additive because that makes it a lot easier. So let's review the method of partial fractions. This is something that you probably saw, God, I don't know in which class, a long time ago. So let's go through it real quick. All right, so the goal here is we want to come up with something that looks like this. So let's say we want this to look something like some constant. We don't know what that's going to be. We'll have to solve for that. Divided by S plus 1, our first term here, plus some other constant divided by S minus 1, plus another constant C3 divided by S plus 2. Right, so now our task is going to be, let's figure out what these constants are. And again, these aren't boundary condition constants or anything, not integration constants. We're just saying we want the left-hand side to look like the right-hand side. So we'll take the method of partial fractions, says let's take the terms in the denominator, assume we can add them together, and then solve for those constants to get the equations to match. Okay, so how do we deal with this? All right, so let's take this whole expression here. And let's call it clear the denominator, right? If you might give you nightmares back to whatever calc class. Clear the denominator so that we're going to multiply both sides by this denominator on the left-hand side. So multiply by S plus 1, S minus 1, S plus 2. Okay, that gives us then on the left-hand side S squared minus 3S plus 4 now equals, let's see, C1 S minus 1 times S plus 2 plus C2 times S plus 1 times S plus 2 plus C3 times S plus 1 times S minus 1, right? So you kind of see what we did. We just cleared out the denominator by multiplying through by everything. Okay, now we can go through and group terms. So let's group things together by, let's see. Yeah, let's just write it just to kind of simplify it a little bit. So S squared minus 3S plus 4 on the left is equal to, let's group by the constants. Let's see. Oh, sorry. Let's expand them out just so we can kind of, that's what we're doing here. So C1, so expanding out these multiplied terms, S squared plus S plus 2. Plus C2 times S squared plus 3S plus 2 plus C3 S squared minus 1. Okay, so now you can use a method really similar to the method of undetermined coefficients. Right, we have different powers of S that appear here. And so we can come up with 3 different equations from this based on the power S to the 0, S to the 1, S to the 2. 3 different equations that we can use to solve for these coefficients. Okay, so if we do that, let's see. So S to the 0 is, on the left-hand side, we have what, 1? 1 times S squared is equal to what's on the right-hand side. It's going to be C1 plus C2 plus C3. Right, C1 times S squared, C2 times S squared, C3 times S squared. And then second equation is going to be on the left. We have minus 3 times S is equal to C1 plus, let's see, 3 C2. And then S2 is going to be 4 is equal to 2 C1 plus 2 C2 minus C3, right? Minus 1 times C3. Okay, so we have three equations, three unknown constants. We can solve for those unknown constants. And now we've transformed our equation into that new form. Yeah. You're right. Thank you. Sorry. Yep. So we can solve for the three unknown constants, and we just have transformed into something that we could actually take the inverse of, right? So yeah, that's kind of the bulk of the method. So then you can go back to the table, take those inverses, and then add them back together. Okay. So let's actually, there's a couple other things here to work through. It's not worth me writing it out, but we went through the case where each of the terms was different. And so you just take the constant over each of the terms. If you have a few other cases you might run into, you kind of need to know how to deal with that. So in case 2, we have repeated factors in the denominator. So if you have something like s plus 1 times s plus 1 times s plus 2, or just s plus 1 squared times s plus 2, here's how you deal with that. And so this is the difficult term here. So here we would have to introduce a term that's a single one of those terms, s plus 1, and then the square root of that term as well, right? S plus 2. So if you had s plus 1 to the cubic power, you'd need each of the just s plus 1 squared, and s plus 1 cubed. Right? So that's repeating terms, and you go through and do the same thing, end up with this solution at the bottom. For case 3, let's say we have a polynomial appearing. So here we have, this is kind of the difficult term here. So the corresponding result there is we would have whatever the order of the polynomial is in the denominator. In the numerator, you have an equivalent polynomial that's one order less. Okay. So here we just have a linear polynomial where in the denominator we have the quadratic. So that's how you split it out, and then you solve it the same way, right? So those are kind of the three different cases you might run into and have to deal with. Any questions on that?